Okay, so now let us have some discussion on advances in incremental farming process. Uh, Now it is a known technology, but during earlier days it was new to the researcher, especially those who are working in the area of stamping and deep drawing. That was having some challenges about the possible LDR ratios and the possible achievements of the dipper cup or forming the dipper cup. So in that regard, some invention took place and some new technology was invented that is called single point incremental forming. I will quickly give the pictorial view of this incremental forming, and then we will go further with the few advances in the different discrete manner. There are a couple of PhD and MTech students have done some work, so I have compiled all these things and that will be put before you, present before you. So this is what the pictorial understanding of single point incremental farming. Unlike our conventional farming process, in conventional farming, the entire seed is deformed with a single stroke of the punch, which is covering the full shape of the cavity, and then ultimately seed wrap around the punch, and you get this cavity form. But in single point incremental farming, small rotating tool or sometimes non-rotating tool moves on the particular trajectory, particular well-defined or predefined path, and then progressively it deforms. I think there is some disturbance, so please mute mic those who have kept the mic on, uh, so that other participant will get this benefit of the presentations properly. So those who have kept
Mr.
the mic
Vikas
on.
Mali, please mute yourself. Vikas Maliji, please mute yourself.
Okay. So let us continue our discussion. So in the incremental farming, it is that the increments or farming takes place at a single point, which is exactly under the tool tip, and then it moves along the particular well-defined or predefined path, and then it goes down progressively, and ultimately the particular shape is formed. So if you see here, the seat is clamped between the holder and the die. Die can be blanking baking plates, and then the forming tool with the rotations or without rotations, it moves on the particular planar surface, and then it moves down progressively, and ultimately you can get the required shape. So this is what the classical way of uh, conducting incremental farming. There are multiple different types of incremental farming. So there may be single point, maybe multi-point, 2 points incremental farming, maybe convex shape, maybe concave shape forming. So all these things are different developments took place in the single point incremental farming, or I would say incremental shape forming. There are few forces parameter. There are of some concern for to the researcher, because ultimately the incremental farming has got certain advantage and disadvantage, we shall see in subsequent slide. But because of certain disadvantage and to overcome some disadvantage, the certain process parameter control is essential. So what are the process parameters? That is nothing but the tool diameter, tool size, tool shape, tool rotation speed, then the feed at which tool is advancing on the planar directions, and what is the incremental depth in the vertical directions, that can be called as z directions, and what is the angle of forming. Usually in incremental forming, it is hard to form the component at a 90-degree angle. Wall angle is the angle of the cup, and then the what is the deeper height of the forming. Compared to the conventional farming, it is observed that the incremental farming gives you better formability. So deeper cup can be formed, but it has got certain disadvantage. So one has to overcome this disadvantage. So same picture is shown here. That is in terms of certain nomenclatures, what thickness is T0, and then final thickness is TF, and then the angle of forming. So and rotations of the tool. Now, what are the advantages and disadvantages? Advantage of SPIF is it can be produced directly from the CAD, and you require only the smaller machine You do not require the die and punch set, and usually it is used for developing prototype and the complex shape, which is resulting into the big, very complex die manufacturing and punch manufacturing. So it is very easy. Those who have complex shape manufacturing and from the CAD itself, you can straight away go for the forming of the seat. There is no need of die, as I told earlier, and it is very fast in change in design. In case if some change in design takes place, then the conventional forming require a change in a die also, and that is very costly affair. So instead of that, simply changing the CAD model, and then you can simply change the program sequence, CNC program sequence. You can generate the required forming, or you can develop the forming. And it most advantage is the, or I would say bigger advantage is it has got very large or high formability. So unlike conventional forming, because it is a bulk deformation, there are chances of reaching to the tensile instability earlier compared to the seat incremental seat forming, where the deformation takes place only on a smaller area, and because of the smaller area, the stress developed is not much compared to the conventional forming, and that will result in the more or higher formability. So you can form a deeper cup also. Even you can have the different, I would say, thinner forming also, or thin thickness also can be achieved. Limitations are, it is very hard to get the forming at an 90-degree angle, because otherwise the tool surface will touch the wall, and that will prevent the formations to 90-degree angle. And the accuracy part, because of the spring back, is always a question, because soon the part which is leaving the contact with the tool, or I should use a different word, soon the tool leaves the contact with the workpiece will start spring back. Hence, the entire tool, the entire surface of the workpiece is progressively undergoing spring back. Unlike in conventional forming, entire seat is undergoing deformations, and entire seat will observe the spring back. Soon the tool is withdrawn. But in the single point incremental forming, as forming takes place only at the particular point that is defined by the tool contact, and soon the tool leaves the contact, the spring back will start. So spring back is also progressive, so that is creating the some complex spring back phenomena. And there is a geometrical inaccuracy, many times it is observed, because wherever you take the deeper forming, means when you take a forming depth, at that point you will find the tool marking, and that also is giving rise the inaccuracy in the geometry. So these are certain advantage and disadvantage. So this is what I just wanted to show you, the some of the I would say this disadvantage because of spring back, and that will result into some inaccuracy in the shape, as well as the dimensions distortions. So this is what the spring back major disadvantage. And to overcome partially, I cannot claim that all these disadvantages are overcome during our journey of almost one decade. We started around in 2011-12. We could not achieve the all the results in favor of achieving or overcoming the disadvantage. But of course, we could minimize the certain or partially this disadvantage. So I will just give you the glimpse of certain achievements. We will start with the first is the parametric studies of SPIF. Now in this parametric study, first of all, we tried with the trial test. Trial test is taking some sample with the seat dimensions, thickness, and then defining the height of the cup or cone, and some radius of a cone, and then incremental depth is defined, and then incremental tool movement in the radial plane along the planar directions. These are the governing parameter, and we try to carry out the very preliminary experimentations. That was in early stage of our journey of research in the incremental farming. Uh, there were a number of different tool part, but we focus on two different tool parts. These are the contour tool path and the spiral tool path. In contour tool path, at a particular plane, tool moves, and then the incremental depth is given. That is, step down is given. Again, it moves along a particular plane. Again, step down is given. Like that, it helps to achieve the required geometry. That is a contour tool path. But in spiral tool path, the even step depth is also done progressively along with the radial change in the planar direction. So it is just like a screwing effect, screw in, screw out effect. That is a spiral tool path. We choose two different material combinations, two different material not combinations. That is for the tail weighted blank. Subsequently, I will discuss that. So two different material we tried, and I will just present before you few of the result or outcomes. These are the tool used for the hemispherical for this forming of the seat, and the baby CNC milling machine at our institute was used because the dimension which was focused was thickness around 1 mm and 1.6 mm or so, and the shape of the cup also was smaller. So we prepared a fixture, and then it was the forming was done on the single point, or I would say the CNC milling machine at our institute. Two different tools were used, hemispherical end tools and spherical end tools, just to understand which tool performs well and which tool should be used for the further uh, detailed experimentations. So during the preliminary experiments, we could able to get some results, and that is to understand effect of tool rotations. We try to check with the six different tool rotations RPM, keeping other parameter constant, and the surface softness was obtained, and it was found that surface softness was around minimum around 1.6 or so micron at the total RPM, tool RPM was around 1250 or 1500. So that was one point where we could able to reach to the conclusion that the RPM, higher the RPM, the better surface finish can be achieved. But still we did further trial. This result was for the one angle of 63 degree. Then we tried with the higher angle also, that is 80 degree, and in 80 degree, that is also giving us the almost similar train, that around 1250 degree, or I would say rotations RPM, the surface finish achieved is minimum. Surface finish, I would say surface toughness is minimum. So surface finish is best. So good surface finish is obtained at the 1250 RPM. So there is one decision parameter that for the detailed study, one can use RPM in the range of 1000 1500, maybe close to 1250. That gives the good surface finish. Then we even tried with the change of different feed as well as different incremental depth, different speed or different feed incremental depth. We tried with different incremental depth of 0.3, zero point 0.5, 0.8. But here I have summarized only two different incremental depth, zero point 0.5 and 0.8. And it is observed that the forming time is always minimum, where the incremental depth is more, and the forming time further reduces. This is the graph for forming time. It is not for surface finish, it is for forming time. And the forming time is further governed by the feed rate. Higher the feed rate, lesser the forming time. Because during the forming, it is not a die punch forming where the production rate is high. It is a single point incremental forming. It takes a lot of time to form one component. You can see here the time taken for forming of one component is ranging from 20 minutes to 60 minutes for the depth of forming of zero point 0.8, and for depth of forming of 0.5, it takes around 35 minutes to 190 minutes. 90 minutes is 1.5 hours, so it is very lengthy or time consuming process. So it at the cost of manufacturing. So time saving is also one of the key aspect or the economical productions. Hence, one result analysis was done that how time can be controlled, or farming time can be controlled, and we could get the result that higher depth of farming and higher feed rate will definitely help the farming of the component. But in that event, by increasing the depth of farming, increasing the feed, there are chances that object may fail before it reaches to the final shape. So that is one other challenge. We shall discuss that subsequently. So that is what is seen here. If you can see that if you have a different depth of farming, here I have summarized two depth of farming, delta Z1 and delta Z2. These are two depth of farming. Delta Z2 is more than delta Z1. And then if you can see, farming is successfully formed when delta Z is less, and as soon you increase the Z, that is 0.5 to 0.6 or 0.7 or zero point 0.8, there are chances of failure. And that is because of the more material has to remove for every incremental depth forming. In the delta Z2, when incremental depth forming is more, the more ringing material will be there, and that will might result into the more forming load, and that might result into the failure. So it is not always advisable to keep the Z high. But on the other side, keeping in mind forming time as the response parameter, one should keep the forming depth Z is high, but to get the successful forming, Z should be minimum. So one has to compromise with this. So that is the one good conclusion, that the forming time can be minimized by increasing feed as well as by increasing the depth of forming. By the same time, by increasing depth of forming, there are chances of early failure. So again, one more result is obtained about the different depth of forming result in the different surface finish. You can see here, we did try with the different surface finish. I have shown here the three different images: 0.2 depth of forming, 0.4 depth of forming, 0.6 mm depth of forming, and you can see that the tool mark Saracens present in the on the surface is bigger for larger depth of forming. Ultimately, that will give rise more surface roughness. You can see here, surface roughness rises or increases as your depth of forming increases. So on one side, for the forming time reductions, one has to keep depth of forming high, but that will result in two different counter effect. That is, the surface roughness also will increase. At the same time, chance of failure also increase. So one is to compromise between these two, and one is to optimize these two. Now, if you see this table, it is reported that the depth of forming beyond 0.5 result in a fracture. So one cannot get the successful forming for the given dimensional forming, or I would say for the given thickness of the sheet and for the given feed, for the given tool rotations, one could achieve the successful forming up to the depth of forming of 0.5. Beyond 0.5 depth of forming, if it increases, the chances of success in forming is reducing. So this is the geometrical comparisons about the desired shape and the different depth of forming. One can see that the larger depth of forming will deviate much from the desired shape. Desired shape is this is desired shape. If you can by chance follow my cursor, this is desired shape, and this is red one and orange one are the two readings which are having lesser depth of forming, 0.2 and 0.3, which are close to the desired geometry, and other two are away from the desired geometry. So for the geometric accuracy also, it is always required to have a lesser depth of forming. So now one has to compromise. There is a third dimensions I am adding. One is forming time, second is surface roughness, third is desirable accuracy. So in terms of accuracy and the surface roughness is concerned, depth of forming should be minimum. In terms of forming time reductions, depth of forming should be high, but one can optimize these two parameters or these two parameters. So this is again the sample of failure. We could get the certain. This is example of trying to form the 90-degree angle, wall angle 90 degree, and all the samples were failed. So we could not achieve 90-degree angle. We could achieve up to 80-degree angle with the 0.5 depth of forming. Then one study was done regarding the process parametrics investigations, varying the four different parameters, rotation speed, because we would like to optimize the combinations. So speed, feed, and tool radial motions and axial movement, that is depth of forming. We did try with the parametric investigations, and in that event, when you change your X and Z into different combinations, 0.1, 0.2, 0.1, 0.5, 0.1, 0.8, or 0.3, 0.2, 0.3, 0.5, like that, in any combinations, that will result in different angle, and it can be understood from this particular figure. When you can see, if you have a 0.5, 0.5 as X and Z depth, your angle of forming is 45-degree. If your X and Z is not same, it is 0.3 and 0.8, it will give rise different angle. So this ultimately results in a different angle. So these are the achievements, target angles and achieved angle. You can see here cone angle achievement, similar target value of the height and target or height achieved. It was targeted to have a forming up to 12 mm depth, and then what is the angle, what is the height we could achieve. The red one indicates the some crack formations in the surface, and these are the forming time. Forming time is minimum here, but one more is there is 7 minute, that is the minimum forming time, where you can see depth of forming is 0.8 and the parameter speed and feed is less, so one can get the successful forming. And the error of angle and height with respect to desirable or target angle and target height is also reported. Now then we tried with the different sets of tool and different tool path strategy. So in this we tried with the four different tool and tool path combinations. We tried with two different tool shapes, hemispherical tool and spherical tool, and control tool path and spiral tool path. With the parameter as discussed earlier, it changed the speed, feed, angle here is changed. Ultimately, the X is controlled accordingly. And incremental depth, because incremental depth and angle will define the X value. X, that is a radial increment to get the cone. These four different combinations, hemispherical tool with control tool path, hemispherical tool with a spiral tool path, and likewise spiral tool. Four different combinations were tried, and the optimum combinations were recorded. And using the ANOVA and Taguchi, we could be able to get the optimum combinations for the parameter level. A, B, C, D are the combinations defined as a factor A, factor B, factor C, and factor D. It is rotation speed, feed, angle, and depth of forming. And then one could be able to get the significant parameter for forming time, as it was earlier discussed that the incremental step is the more contributions significant parameter, as well as feed. For cone height and for cone angle, wall angle is the incremental significant parameter. Here only three different combinations are summarized out of four. Then profile accuracy was obtained. This is the profile of the cone at the particular plane. It was recorded. 46 equidistance points are measured to get the profile. This profile is compared with the target profile. Profile error at the for all 9 experiments in the L9 array was compared, and the error are recorded. An error of HST-CTP stands for hemispherical tool will control tool path result in a minimum. Hemispherical tool with spiral tool path is next highest, and then spherical tool with spiral tool path is the highest. So these are the three result comparisons. So This helps us to decide which should be the path profile. It should be hemispherical or spiral, and what should be the tool. So one can make control tool path, that is giving rise the minimum profile error. So profile accuracy is key aspect. It is one of the disadvantages. So that is to be overcome. So this particular result helps us to arrive at the some conclusion saying that hemispherical tool will control tool path, or hemispherical tool will be the spiral tool path. That these two are the better options compared to spiral tool path. So for further study was done using this tool path. This is the comparison of profile error uh, at different locations. You can see there are three locations are marked here. One is near flange, one is in the wall, and one is at the bottom. And one can very clearly make out that this orange line is a target or designed shape, and these are three different paths. And you can see the tool path are all tool paths are giving very close agreement with the desired shape so far as wall is concerned, near wall. But soon if you take the path near flange, accuracy near flange, it is deviating much. If you see here the hemispherical tool with the contour tool part, that is this orange dotted line, is very close to the target geometry, and it has got minimum pillowing effect. This is called pillowing effect. Pillow, just like our conventional pillow, when you put a head on the pillow, the edge of the pillow gets pressed and the center part of the pillow remains near the undeformed conditions. So same is the situation here, just like you are putting the head on the pillow, and that gives the pressing effect here. It does not have a pressing effect here. So you can see that the pillowing effect is minimum for the hemispherical tool contour tool path. So out of three, geometrical accuracy of hemispherical tool contour tool path is best in the formed area, except near flange. But near flange also it is reasonably same for all three different tool paths. So same is discussing. I'm just skipping this. Then we did the final experimentations. This final experimentations is done much more detail. That we have used hemispherical tool and contour and spiral tool path, because we could eliminate now the spherical tool, only hemispherical tool with both the tool path. And then we tried to add one more parameter, is the tool diameter is added along with the wall angle, feed, increment depth. Tool diameter is added, and then we tried to find out the result, compiled results. We did the trial 2 times for each combination of hemispherical tool, contour tool path, hemispherical tool, spiral tool path, and results are reported here. And the shape formed after forming are also shown here. It is quite a good match, if one can see, except the close to flange. Close to flange there is a deviations, so that is another aspect to be controlled. But otherwise, right from the -2 depth till its full depth, the shape of the cup is very close to target shape. So that is what the result. One can control the spring back or geometric accuracy by varying the parameter. These are a few photographs of forming done at different angles. You can see 90-degree angle, present study, we could not get it. Even 80-degree also, some components are failed. We could get failure in the straight failure as well as zigzag failure, just to correlate with the similar result finding in the literature. You can see failure can be of straight failure. There are some in 2012 has done study, and that is similar in the agreement. Similarly, zigzag failure also is achieved in our case, that is comparable to the other research done in 2004. So that is what, just to highlight the different types of failures. Then we extended study with the profile error estimations. It is only regressions formulations, and the comparisons are done with a few cases where hemispherical tool with control tool part, hemispherical tool with spiral tool part. Both the tool parts are compared with the model and experiments. This is just to get the idea about intermediate performance, because in the experimentations we did the discrete and study. We took depth of zero point 0.5, we took a depth of 0.5, 0.25, and 0.75. What is the behavior if you have the depth in between this? Just to get the idea about that, this particular regressions analysis or empirical formula uh, will be helpful. So that is the only objective. Otherwise, this is just to add on the what you can say part of achievements. So these are three different feeds at which this trial was done: 75 mm per minute, 150 mm per minute, and for all these three different feed, agreements are there between the experimental results and the model results. Then, very recently, we did some investigations on single point incremental forming of tailor-weighted plank. Tailor-weighted plank is having the very good applications in the area of automobile, where weight reduction is one of the key objective. So tailor-weighted plank is having the more acceptance in the automobile sector. I will just give you the couple of example. Before that, let me introduce what is tailor-weighted plank. By chance, if you are aware of that, it is fine. Otherwise, those who are not aware of this, that will be new to them. So that tailor-weighted plank is nothing but where blanks or where multiple sheets of different materials or maybe different thickness are welded together prior to forming process. So here you can see the image, green and the orange color or little pink color. These two are welded. These two materials can be same, material can be different, thickness can be same, thickness can be different. So any combinations is there, but it is always classically different thickness of same material or different material of same thickness. So these two materials or maybe more than two materials are welded before forming, and then forming is conducted. Then material is formed. Now in this particular case, the classical error is, I would say the drawback is, as the materials are different or as the thickness are different, the forming of materials would be different, both the sections A and B, or green and pink, or green and orange. So that will result in the different heterogeneous deformations. Hence, the weld line will shift. It will no longer remain where it was before forming, and that is one of the key issue about the TWB forming. Application parties, you can see here, these are the applications of automobile sector. I'm not going in much detail of that because our objective is to discuss about single point incremental forming of TWB. So I would focus much on the analysis part. This is what the I was just referring to. This is a door panel. I would say door, car door. You can see it is always hinged somewhere over here, and this is the handle portion. So near the hinge, one should have a stronger material, and the otherwise other area one can have a thinner or weaker materials. That is what is shown here, and this is the weld line, weld joint. Now, if this is to be deformed, maybe stamping is to be done, or the forming is to be done for this, then it is always a challenge because materials are different or thickness are different. That will result in a different forming. As different forming is there, the thinning will be different, spin back will be different, and ultimately geometrical inaccuracy will be there. So to control that, one has to carry out the analysis. Advantage and disadvantages. Advantages, interior will be advantages. It reduces the weight because not entire section is to be of heavy weight, heavy material. It can be thinner or the lightweight materials can be used wherever stress develop is less. That will reduce the weight. Ultimately, it will increase the fuel efficiency. It controls the direction strength at particular locations. Wherever stress develop is more strength material can be provided. And as the material weight is reduced, cost of material also will be less. So these are the advantage. Limitations part is uncontrolled spring back, uneven spring back, weight line shift, and formability is reduced because formability is decided based on the combination of two material. It is not only one material. As these are two different materials, formability will be different. It will not be formulate of any single material. So that will always be a challenge. So that is what the challenge of TWB, and we try to address partially this challenge using incremental seed forming. So this just skipping. So we did similar story because the first part is the fabrication of TWB and then forming of TWB. So that was a challenge. So we tried with the similar story and then later on we tried with the uh, experimentation part. So I will just give you the glimpse of the uh, outcomes. We tried with the parametric study. We changed the strain coefficient and the strain index and the thickness ratio and the yield stress ratio because we are going to use two different materials. So two different yield stress will be there, two different thickness will be there. So two different N and K will be there. So we try to use these combinations. Here ratios are used. You can see ratios are always thick to thin or strong material to weaker material. So strong material is always considered as a material which has got higher yield stress, and weaker material is having lower yield stress. And like this, thickness ratio are used. And then we carried out the investigations. Now in TWB, the important aspect of analysis was from which point tool rotation should start. So we made a decision of choosing four different tool starting point. Tool starting points are SC stand for strong material center, WC stand for weak material center, WTW stands for weld to wick, means starting point is on weld line, and weld to S, WTS is a starting point is on weld line and tool is going to a stronger material. So these are the four different combinations we tried. And then control tool part, as it was discussed earlier, the result was found to be more better in the hemispherical tool with the control tool part. So same strategy was extended here. Geometry was taken as a cup cone and circular cup, and then the forming was done. This is the observation of weld line shift. One can notice here that weld line is deviated. You can see it is a vertical line, it gets deviated. It's very clearly visible here. Weld line is deviated. These are tool motions, tool path for the tool motions on the panel directions. Now, this particular weld deviations, the weld line shift, can be shown here. Dimensions where you can see this is the weaker material. This is the example of weak center WC. Tool is starting from weak center point and it moves in the direction of green arrow. After completing one circle, it will further go down. Depth is given. Again, it will complete second circle like that. It will form the curve. Now, in this activity, the tool is moving from weak to strong, and even in the stamping operation also, when you perform the stamping, weld line will shift towards stronger material because weaker material is forming more than stronger material. So weld line always shifts towards the stronger material. So same is observed here, but you can see the deformation is much more in this area. Displacement is not much in this area. It is more because there are two different phenomena acting here. Weld line shift is due to the combination of weaker and stronger material. Weaker material will have more deformation than stronger material. So that will result in the weld line shift towards stronger material. But at the same time, because of tool motion, tool dragging will take place. Tool dragging will take the material further along with the tool bottom. It will not be removing our material, but because of friction, it will try to direct the deformations further in that area, which can be seen if I see the enlarged view of the same A and B. This A and B is enlarged here. You can see, you can make out very clearly. that this is the tool, this is the deformation because of material forming. Weaker material will deform more than stronger material, so both the directions will have a deformation. But here, this blue arrow indicates a tool dragging. Tool dragging means it will try to take the material further in the stronger side, but after reaching to strong center, tool start reversing, and that will have a reverse phenomena, and that will give rise some more wheel line shift in the weaker material. It is unusual, unlike what is observed in the stamping operations. So that is one of the key information we could get it when single point incremental forming was conducted on TWB. Then all four cases were compared for the minimum weld line shift, minimum plastic strain, and minimum thinning. And it was observed that weld to strong combinations means tool starting point is on the weld line and moving towards strong give rise minimum weld line shift, minimum plastic strain, and minimum thinning, because thinning should be less. If harder thinning, more chances of failure. And the contribution of the each of these combinations are shown here. And we are not going much in detail of that, but one can make out from here that thickness ratio and yield strength are having more contributing parameter compared to strain index ratio and strain coefficient ratios. So these two are the more governing parameter to get the minimum weld line shift, minimum plastic strain, minimum thinning. For all these combinations, same is the observations. You can see here, same is the observations. And the optimum combination is obtained. You can see it is very easy to make out. Only C and D are nothing but the thickness ratio and yield strength ratio are the optimum combinations. Common -1, -1, -1, -1. That is the label. -1, 0, and 1. These are the label which is used for L9 orthogonal array for each of the starting positions. So the 4 starting positions. For each starting position, 9 different tests were done. So total 36 tests were done. Then thinning analysis was done. This is just to highlight the simulation results of thinning near boundary and the thinning near the weld line boundary, that is seen here for different starting positions. SC, WC, WTS, WTW, almost similar thinning is observed. Main thinning is observed depends on the tool starting point. You can see this is a thinning of green line. By chance, if you can follow the cursor, this is the thinning because of these tool starting positions. SC stands for tool is starting from the strong center. So there is a tool mark. Same is observed in weak starting point. But here, the starting position is on the weld. So this is the weld thinning. You can see this is a weld thinning. Also, this very faint line is a weld thinning. Then this is the result of simulation number 3 out of 9 simulations. This is the result of simulation number 6. Simulation number 6 is very clearly indicating the thinning on the weld line. You can see because the starting position is on the weld line. Thinning on the strong center, thinning on the weak center. That is because starting position is strong and weak respectively. Then confirmation geometry was done about the different combination of SC, WC, WTW, and WTS. The target geometry is shown with the green color here, and the 2 different shape sections were plotted here. Now here, 2 different sections are what? 2 different sections are orthogonal to orthogonal to weld and along the weld. Here the SC stands for tool is starting from the strong center. So tool starting from strong center means this dotted line which is shown with a black color. This dotted line shown in black color is along the tool starting point, orthogonal to weld line, and WC is orthogonal to tool starting point and along the weld line. Now if you see, if you are plotting the profile along the tool starting point, which is shown with the this black line, it is deviated much with the green line. But if you plot the tool geometry at the orthogonal to the starting point, then that will have a much clear agreement with the target geometry. Same is observed here. This is a WC, means weak center starting point. Weak center starting point orthogonal to whale means parallel to starting point. It has deviated more, but near the starting point, it is I would say orthogonal to starting point. It is not deviating with target geometry. Same is very clearly visible for WTS and WTW. WTS and WTW means starting point is on the whale itself. When starting point is on the whale, the orthogonal to whale is going to give you more agreement, and the along the whale, because of the excessive pressing at the starting point, it deviates. So this indicates that one should not have the cross sections comparison uh, along the starting point. If you take the comparison along the starting point, it is bound to get deviations. But if you take the comparison across orthogonal to the starting point, irrespective of SC, SC, WC, WTW, WTS, it gives close agreement. So we did try with the angular positions also. So different angular positions we tried. This is the starting point for strong center. This is whale's starting point, maybe towards weak, maybe towards strong. And in between, three different points were taken at angle of 30 degree, 45 degree, and 60 degree. And then results were plotted. You can see here the results. These results are very clearly indicating that the if you take the plot uh, along the starting point, that is SC, along the starting point, that is SC, dotted line, black dotted line is the target geometry, and SC is a geometry which is taken at the starting point in the strong center. It is deviating much compared to other. And if you see, eventually as your angle of starting point increases 30 degree, 45 degree, 60 degree, and ultimately WTW, then the deviation is reduced, you can see, and it is in agreement with the target geometry. So that is giving us very useful information that to control the geometry accuracy, uh, one should decide the starting position not strongly on the center, center on a strong center or weak center, not even on the whale line. It should be at certain angle that will give you more better performance, or your measurement should be at the certain sections, cannot be, should not be section aligned with the starting point. So that was the study of the geometry accuracy. Then we did try with the individual parameter effect. These are very simple because the analysis or the experimentations simulation was already done. It was only plotting the results. So it indicates that thickness ratio and yield strengths are more influencing on the whale's land shift and personal thinning compared to other two parameters. It was already discussed earlier when we could discuss about the contribution of parameter. Contribution of thickness ratio and yield strength ratio is the maximum compared to the contribution of strength coefficient ratio and strength index ratio. This is the study extended for the lubrications effect. Lubrications, we did try with the two different lubrications. One is with the low frictions. This simulation study only, so there is no actual lubrication used. Did try with the different coefficient of friction. So the coefficient of friction was used as 0.1 and 0.5. 0.1 is the low frictions, 0.5 is the high friction. And one can notice here that because of the lower friction, the tool dragging effect is less. Because of higher friction, which is shown with the green color, the tool dragging effect is more, and that give rise a differential well line shift. So to control a well line shift, one should also control the coefficient of friction. So that is the outcome of this particular finding. Even we did investigations on the heat assisted single incremental farming, but I am not reporting this particular result because it is under further investigations for the PhD. So it is IPR concept, IPR fit case. So I don't want to disclose that right now, but we could able to get the differential well line shift for different temperature of heat assisted single point incremental forming. Sorry to not giving that particular result here. Then in this study, that all these are the simulation study, but we did try with experimentation also. And in the part of experimentations, we first try with the checking with the grid marking methods, because in metal forming, to estimate the strain or to obtain the strain value, grid marking is one of the way of getting the strain analysis. So we did try with two different grid marking. One is UV based grid marking, and one is laser based grid marking. And we did compare the results of both the grid marking. Grid is mark of circular section, circular size of 2 mm diameter, 5 mm diameter. Different grids were plotted on the surface of the sheet, and one could observe that the forming height obtained using the grid marking. Grid marking doesn't give the different forming, but because of grid marking done using ultraviolet as well as with the laser, there is a chance of some change in material property or some change in material thickness. Hence, ultimately, eventually, it will result in the reaching the failure early. So here, this table, this particular bar chart shows how successfully we could able to form the cup, which is marked with the laser marking as well as the ultraviolet green marking. One could see here that UV marking gives more forming height for each of the blank thickness 0.51 and 1.67, and forming height for the ultraviolet UV marking, all are formed successfully, but laser mark component are failed. So that indicates that there is some internal change, might be in the material property, might be in the thickness of the sheet taking place under laser marking, and that results into preventing or reaching to failure earlier compared to the UV marking done on the surface of the sheet. These are the similar results obtained for minimum thickness. This was earlier was for the height. This was for the formed thickness. One can see thickness formed is almost similar 0.33, 0.66, 0.77. So between UV and laser marking, there is no much variations. But for the variations in terms of minimum thickness is achieved, wherein you can see that the laser marking has got the chance of failure earlier because of thinning takes place. But that is not much of concern, because once failure is there, it is failed. So there is not much concern about that. These are the pictorial image of the formed component, uh, and these are the showing the tool marks on the wall of the cup that indicates serrations, or that indicates the some surface roughness indications because of tool marking when you give the depth of forming after completing one contour of forming. This is the forming limit diagram plotted for the UV and laser mark, and it is observed that UV mark component has got higher forming compared to the laser mark UV component. Laser mark UV component are having the more chance of failure, early failure I would say. Laser UV mark component can be formed little deeper, and that was already presented earlier in the couple of slides before. Then welded blank single incremental forming was done. Same hemispherical tool was used. I'm just rushing to this particular thing, and this is the actual image of formed component. Experimentation is done. and weld line shift is observed. It is just to validate or to verify the simulations finding, because experimentation is costly. So one cannot conduct experimentations for different parameter much in detail. We have to go with the certain design of experimentations, but still it is required to be extended further by verifying the simulations. So once simulation is verified, one can always find out incremental parameter effect based on simulations. So this is the pictorial image of the experimentations results of weld and shift. Four different combinations were tried. PQRS. P stands for 40 feed and 1.7 thickness. Q stands for 28 feed and 1.6 thickness, and likewise R and S. And the weld line shift, average weld line shift, is recorded here, and it is observed that for uh, the P combinations, the weld line shift is minimum, and R also is second minimum, and that is for higher feed and lower, I would say higher feed, and for both the thickness. Lower feed has got more time tool is spending at the particular locations with contact with the seat, and that may result in more tool dragging or the seat dragging. Higher feed will have a minimum time spent by the particular tool contact with the seat, and eventually that will result in less dragging. That is what the one can make out the observation from this. This is the failure analysis. Failure is reported here. One can see this is the, by chance, if you can track the cursor. I am moving the cursor just to help you look at the failure. This is a weld line. Prior to forming, welding is done, and when forming is done, welds are open. You can see these are the open portions. Weld gets teared off. These are separated. All this is failure. So it is just to indicate how failure will localize. Localized failure is observed. So this is what the failure image. Again, few more failure images are seen. Actually, this is because of the poor welding. Whatever is welding is done, it is because of poor welding. These welds are open. You can see, because this is the bottom of the cup, and bottom of the cup is not undergoing any deformations, because tool is not coming in contact with this bottom deformations, bottom portions. Only tool moves on the wall, but still there is opening, because ultimate stretching will take place, and this stretching will open up the welding if welding is not done properly. Hence, this helps us to find out what should be and how one should carry out the welding prior to forming takes place. These are the thinning analysis of the different combination PQRS. That says that the thinning is more for the experimentations observed compared to limiting thinning as well as thinning based on sign law. This thinning, limiting thinning, is based on the ultimate tensile instability of the material, and sign law is based on the geometrical angle. But in this particular case, we could able to achieve more thinning. Actually, more thinning is not advisable, but only message here is, in spite of getting more thinning, material is not fail. So one can go beyond the limiting condition of thinning based on the tensile stability to get the more formability. That is what only the takeaway from this particular graph. Same as the surface roughness values, where dummy seat is used on the seat, so that the seat is not coming directly in contact with the workpiece, or sorry, with the tool, and dummy seat is deforming the actual seat. And surface finish is observed. It is found that the surface finish is best or good when dummy seat is used, and without dummy seat, surface finish is poor. Then the lubrications, what it was simulated, same was tried here with lubrication, without lubrications. With lubrication, surface finish is good compared to without lubrications. It is just to have comparative assessment What simulations results are giving us the results? Are we getting the same line of results in the experimentations? And answer is yes. Value cannot be compared because value uh, needs some exact parametric parameter or the material parameter in the simulations. So we are not comparing exact value of simulation result with the actual result. Only train is compared here. Two different lubrications conditions without lubrication, with lubrications are compared, and it is obvious that the surface finish with lubrications is better than without lubrications. Then effective tool initial positions, I just would like to recall about our earlier discussion of four different starting positions. SC, WC, WTW, and WTS are tried experimentally also, and these are shown here experimental results. It is just to give you the confidence that not simulation study only alone is done. Experimentations were also done, and these are reported here. This is a well done shift is shown on the larger image. Uh, I'm just simply scrolling these slides because images are similar. Only value wise, magnitude wise, and direction wise, it might differ for different starting positions. You can see, you can make out starting positions on the rail. In earlier case, starting position was on the on the either weak material or strong material. This is WTS, this is WTW, fine. And then the compressor well line shift was done, and it is observed that the well line shift is found to be minimum in the WTS conditions. Next minimum is WTW, means well too strong and well too weak gives the minimum well line shift compared to strong case, strong center and weak center. And simulation results also in the similar trend where WTS and WTW gives the minimum well line shift, minimum thinning, and minimum plastic strain. So experimental finding and simulation findings are in the same trend. We cannot have exact comparison of the magnitude. As I told you earlier, parameters are supposed to be accurate to conduct the simulations. These are the uh, additional images just to uh, have more validations of the experimental findings. I'm just scrolling. This is the forming limit diagram drawn experimentally for the different combinations. Even parent material independent FLD was also plotted, and you can see FLD plotted for the parent material independently is having lower formability compared to the formability obtained on the different starting point WTS, WTW, WC, and SC. Highest formalities obtained in the case of SC, but that is only for selected cases. Otherwise, only takeaway from this particular graph is that uh, the TWB and incremental seed forming uh, has got the higher availability, or I would say higher formability compared to the forming of independent seeds. This is the thinning analysis. It was reported earlier also, but here for the experimental graphs, one can see here for the different tool starting positions, and it is found that compared to individual material, thinning is observed to be more is without failure, without reaching failure. So that is considered as a bit, I would say, safe deformations. Still, material is not failed, but thinning is higher than uh, the thinning of independent material or individual material. So this is the same analysis for surface toughness. Surface toughness of sorry, WW and WTS is found to be minimum compared to SC and WC. This is in a similar agreement with the simulation results. Force analysis was conducted. I will just take a couple of slides before I close my presentation. Force analysis was also conducted, and in the force analysis, the forces were recorded for the forming of simple homogeneous blank of made of same material. Two different materials were tried, and then welded blank were formed, and it is observed that the pattern is similar. But if you just have a close look, then you can very clearly see that red color and black color are the forming forces recorded when forming is done of simple single material. But when forming is done of a TWB, which is made of these two material, red and black, then the pattern is somewhat different. Different pattern is because in the simple material or single material, there is no weld in between. Hence, as there is no weld, material forming will take place. Variations of forming force will take place in the band of around 100 Newton or maybe 150 Newton. But if you see the green color is a train of the forming of TWB. In forming of TWB, forming takes place of a weaker material, then weld material, and then strong material. And when it is done, it depends where is your starting point. If a starting point is on the weld point, then force would be different. If starting point is center of any of the weak or strong point, the forming force pattern would be different. Here you can see that when material is forming, weak forming or strong forming, it has got variations, and there is a sudden drop in the force at the junction or at the joint, and then again it rises, and again it drops, and again it rises. So that pattern is different than the pattern recorded for the forming of the single blank. Still, the investigation is on. We are unable to have a conclusive remark right now that why the force at the weld junction is dropping. Why not it is increasing? Why not it should increase? Because weld is always considered as a strong joint compared to the weld of compared to the weak material or strong material. But sometimes it is observed in tensile testing that the if welding is not properly done, then weld strength may not be comparable with the either of weak material or strong material. Hence, that might be the reason that might be some drop of the welding, the forming force. So this is what the uh, portions I just wanted to present before you. There is one more study extended, but it is with the conventional forming. So I think it will not be much appropriate because it is again with the limit dome height test comparison with single point forming. It is just to show you the image. I will just take 2 minutes to show you findings of this. You can see limit dome height test results are in agreement with the SPF, but SPF has got the different weld line shift, just like a sinusoidal weld line shift compared to LDH. And then forces are compared here, forming forces are compared. These are the references used in the study. 3 PhD are produced out of this work. And ultimately, finally, let me thanks all the participants for presently listening to the presentations. And I would be happy if I can be of some response to your query. Still, the journey is on. Students are showing interest of taking this particular technology further. Professor S. Kumar, who is the coordinator of this particular this short-term program, is also very much into this particular study of incremental forming, and a couple of students could able to do doctoral study under him also. So ultimately, in the summary, I would just like to wind up with the statement that the SVNIT Mechanical Department manufacturing section is actively involved in the sheet metal forming with the number of students registered for PhD and number of projects sanctioned by funded funding agency. So with this, let me thank finally